In this section, we will introduce the bending stress in beams, or the stress in a bended beam. Right, so normally we use the Euler beam theory to describe the behaviors of a bended beam. Okay, it describes the relationship between the beam's deflection and the applied load. One important assumption is the flat plane perpendicular to the longitudinal axis remain flat after applying loads. Okay, this assumption, as we mentioned in the beginning, this is called a flat plane assumption. It is associated with the first important assumption, that is the small deformation assumption. Right, so when the deformation or the deflection of a loaded beam is very small, so we can ignore the curvatures applied occurs to the planes. Okay, so we will just assume that it will just remain flat. Okay, what does that mean? Let's look at this example. Okay, we have a simply supported beam as shown here, and it's loaded by a random concentrated load F. Okay, let's look at a section of the beam AABB. Okay, as shown here, this is we cut this out from this loaded beam, the AABB. This is the beam section. Okay, so after this loading, as shown here, after the loading, this beam will be bended, and it will be deformed. Okay, to give you a curvature as shown here. So this section AABB will be bended too. Right, the shape will become this. Okay, so AA will become A prime, A prime, and BB will become B prime, B prime. Okay, so our flat plane assumption just means that the AA is a straight line, right? After deformation, the A prime is another straight line or flat plane. Okay, so this is the flat plane assumption. So in this case, since deformation is very, very small, we ignore the curvature and we assume that AA and A prime, BB, B prime, B prime are all straight lines. What does that mean? Okay, let's just focus on this beam section. As shown here, let's focus on this beam section before deformation. It's a rectangle, and after deformation, it becomes A prime, B prime, B prime. Okay, please think about these several questions. The first one, from AB to A prime, B prime on the top here, is the fiber become longer? Does the fiber become longer or shorter? Okay, from A to A prime, from B to B prime on the top, this fiber becomes shorter, right? It is compressed. And on the bottom, it's stretched, right? From this A to that A prime, from this B to this B prime, this AB bottom fiber is stretched. Since the A prime, AA are both straight line, right? So here, if we look at the deformations on a random point, it must be directly proportional, linearly proportional to the distance to a neutral point here. Okay, let's analyze this problem in several steps. Okay, in the top fiber, it is compressed. It becomes shorter, right? Meaning that the strain is positive or negative? Strain is negative, right? So how about the stress? Stress is also negative, right? Because of the Hooke's law, right? Just stress is just equals E times strain, normal strain, right? So here's this stress and strain on top are both negative. How about on the bottom? Since the fiber becomes longer, the strain is positive, so the stress will also be positive. Right? Then do you think there is a point where the stress and the strain are both zero? Of course, when you have a transition from a negative to a positive strain or stress, there must be one point at which the stress and strain are both zero. right? On AA, that is this point. On BB, that is this point. And on any other planes between A and B, you will have this kind of points. If you connect all of these points together, right, so you will get an axis. Right, this axis is called a neutral axis. Right, along this neutral axis, stress and strain are both equal 0. Okay, as we also mentioned, at another random point as shown here, so from the neutral axis, you're moving towards the top or moving towards the bottom. While this at a random point, the stress and strains are just linearly proportional to its distance to the neutral axis, right? Because of these similar triangles. Okay, so as a summary, as shown here, the stress and the strains are linearly proportional to their distance to the neutral axis, and they are 0 at the neutral axis, and they are maximum on top and on the bottom, and their values are opposite below and above neutral axis. Because of this linearly proportional correlation, we got this equation to calculate the stress. Okay, the normal stress because of bending, induced by bending, normal stress equals m, the bending moment, times y. This is the distance of this this point of concern to the neutral axis over I. The I is the moment of inertia. Okay. So its maximum values, the maximum values is equals m times c over I. Right? The c is the maximum value of y. Right? So in this kind of beams, this just appears on top or on the bottom. Okay, we have an alternative form of a stress equation, that is sigma equals m over s. Right, this s here is called section modulus. It is used to calculate the maximum values of the bending stress. Okay, the s has two values, on top and on bottom. Right, on top, it's just I over c top, and s bottom equals I over c bottom. Right, the c top is just the distance from the top to the neutral axis, and the c bottom is the distance from the bottom to the neutral axis. Okay, knowing these theories, we will summarize the algorithm of determining maximum bending stress in beams. Okay, determining maximum bending stresses in beams, these are very practical problems in design. Right? Of course, in tests, right, we also request you to calculate the stress values at random points on a cross section. Okay. Here we assume the bending moment is acting about the horizontal axis. Then the step 1, we will analyze the structure and determine the moment diagram. Okay. The step 1 is the moment diagram. Okay. Step 2 will be determine centroid and the moment of inertia. We have reviewed in the beginning of this lecture, right, is how to find y bar and the I. Right, this is for a simple cross section like a rectangle or circle. This is very simple. But for composite sections, you just need to use these equations and the two tables. Right, y bar is normally what we need to determine. X bar sometimes needed, but in most cases, we do not calculate x bar. And this is the equation to calculate the moment of inertia. Then in the third step, we will determine the bending stress. It can be positive or negative. Positive maximum moment, maximum tensile stress and maximum compressive stress. Well, they are both calculated from this equation m times c over I. But you just need to identify on which side you will have compressive stress, on which side you will have tensile stress. Okay, if these are clear, for symmetric sections, the C will be the same. Right, the C will be the same. You just need to identify the signs of the stress on each side. And for non-symmetric sections subjected to positive moment, you will have the compressive stress on top. Right. If it's subjected to positive moment, you will have negative stress on top, compressive stress on top. Right. You have the maximum tensile stress on bottom. If it's subjected to negative bending moment, okay, on the top you will have the maximum tensile stress. On the bottom you will have the maximum compressive stress. Okay, if you have more than one bending moments, you have some local maximum bending moments, so you may do several calculations and compare the maximum compressive stress values and maximum tensile stress values and find the maximum one. Okay, so here you may feel this is very confusing, but we actually give a very simple method to remember the signs, the sign conventions last time, right? So let's review that stuff. It is how to quickly and correctly remember the positive and negative thing. Okay, positive bending moment, negative bending moment. So when it's subjected to positive bending moment, what is the positive bending moment? Okay, positive, when the beam section is subjected to a positive bending moment, this positive bending moment will make it cry, right? So your beam section after deformation will make it smile. Okay, since when you feel something positive, you will smile, right? So a bending moment will make the beam section smile. Okay, so when it's smiling, on top of it, look at the fibers on top of it or above the neutral axis, the fiber will become shorter. Right? It will become shorter, so the fiber will become shorter, so the stress will be in compression. And on the bottom of it, since the fiber will be stretched, so the stress will be positive in tension. Right? So this will be someone that is smiling. Right? This is a positive bending moment. So how about it's subjected to negative bending moment? And to have negative bending moment, it will make the beam section cry. Right? So when it's cry, on top of it, the fiber will be stretched, so the stress will be positive, and at the bottom of it, it will be compressed, so the stress will be negative. So you will get someone that is crying. Okay, so then you can compare these two faces to these equations. Right, when subjected to positive bending moment, you have top negative, right? Top negative here, and bottom positive stress here. Okay, when you have negative bending moment, you have this crying face. So on top of it, it will be positive, and bottom of it, it will be negative. Okay, easy to remember. Then let's go through several examples to do some practice.